You clap your hands in a big empty room. Clap. And a moment later, you hear it again. Clap. That second sound can feel a little spooky, almost like the room is talking back to you. But of course, the room isn't talking. So, what's really happening? Today, we're solving the mystery of the echo. To figure this out, let's think like a scientist and follow the sound, like a detective following footprints. First, what even is sound? You can't hold it or see it. Sound is a movement. When you clap your hands, you're pushing the air around them, causing it to vibrate to shake back and forth really fast. These vibrations travel outward in all directions as waves. Think of it like dropping a pebble into a pond and watching the ripples spread out. Sound waves are just like those ripples, but they travel through the air. So when you clap, these invisible waves spread out from your hands. Some of them travel directly to your ears, and that's the first sound you hear. But the waves don't just stop there. They keep on traveling until they run into something, a wall, a cliff face, the side of a big building. And here's the most important part. Sound waves can bounce. When a sound wave hits a hard, smooth surface, it reflects or bounces off, just like a ball bouncing off a wall. This reflected sound wave then travels all the way back to you. If it reaches your ears, you hear the sound for a second time. That second sound is the echo. So, an echo is simply a sound wave that has bounced off a surface and returned to its source. Now, you might be wondering, why don't we hear echoes all the time? In our living rooms? Or in a classroom? That's a great question. It's because our brains can only register an echo as a separate, distinct sound if there's enough of a delay between the original sound and its reflection. If the bounce comes back too quickly, your brain just blends the two sounds together, and you perceive it as one single, slightly longer sound. This is called reverberation. To hear a clear, distinct echo, you need distance. The sound wave needs to travel for enough away and back again to create a noticeable time gap. This is why you're much more likely to hear echoes in big, open spaces. Think about canyons, mountains, large empty auditoriums, or even tunnels and parking garages. But distance isn't the only thing that matters. The type of surface is also super important. Hard, smooth surfaces are fantastic at reflecting sound. Things like concrete, stone, tile, and metal act like mirrors for sound waves. On the other hand, soft, fluffy surfaces are sound absorbers. Carpets, curtains, couches, and even people in a crowded room soak up sound energy instead of bouncing it back. That's why an empty apartment sounds so echoey. But once you fill it with furniture and rugs, it gets much quieter. Let's do a little thought experiment. Imagine you're standing at the edge of a huge canyon and you shout, "Hello." Your voice travels across the vast open space, hits the far rock wall, bounces off, and travels all the way back to you. A few seconds later, you hear a clear, crisp copy of your voice, "Hello." That's a classic echo. Now, imagine you're in a dense forest and you shout the same thing. What happens? Well, the trees, with their rough bark and countless leaves, aren't smooth, flat walls. They scatter the sound in all directions and absorb a lot of its energy. The sound that does come back is messy, weak, and jumbled. You might hear a faint, muffled response, but you won't get that clean, sharp echo you heard in the canyon. What's really fascinating is that we can use echoes to do some incredible things. Because we know the speed of sound, it's fast, about 343 meters per second. But not instant. We can use echoes to measure distance. If you time how long it takes for an echo to return, you can calculate how far away the reflecting surface is. You just have to remember that the sound made a round trip, there and back. This is the exact principle behind some amazing natural and technological systems. Bats are masters of this. They send out high-pitched squeaks and listen for the echoes bouncing off insects and obstacles. Their brain uses these echoes to build a detailed sound map of their surroundings, allowing them to navigate and hunt in complete darkness. This is called echolocation. Dolphins and whales do the same thing underwater. Humans have borrowed this idea for our own technology. Submarines and ships use something called sonar, which stands for sound navigation and ranging. They send out sound pulses, or pings, and analyze the returning echoes to map the ocean floor and detect other vessels or objects. Underwater, even in medicine, ultrasound machines use the same basic concept, sending safe, high-frequency sound waves into the body and using the echoes to create images of organs and tissues. It all started with a simple bounce. So, let's wrap this all up. A sound is a wave of vibrations traveling through the air. When this wave hits a hard surface, it bounces back. If there's enough distance for a delay, your brain hears this reflected wave as a second, separate sound and echo. Now for a little challenge. Next time you're in a place that seems like it might make an echo, a big empty hallway, a tiled bathroom, or a quiet stairwell, try it out. Just give a single, sharp clap. Listen carefully. Do you hear a second sound? If you do, think about why. Is the space big enough? Are the walls hard and smooth? When you start to understand echoes, you start to hear the world in a whole new way. You realize every space has its own unique sound signature. An echo is just sound, doing what it does best, traveling, bouncing, and telling a story about the world around you. Thanks for watching.